In these times of lockdown, all of you have surely valued the importance of resilient communications. In all our communications, being it voice, data, broadcasting, we are making use of optical fiber networks, wireless networks, but more and more satellites are an important element in telecommunication networks. And even governmental and military customers are using more and more infrastructures where space assets are a very important element of it. Typically, especially for telecoms, this was done with big satellites, but more and more telecom operators are now relying on constellations of small satellites. These small satellites have indeed been booming in the market very recently, thanks to miniaturization. This has allowed satellite manufacturers to really augment either their large satellite systems, or to really replace large satellites by very performant smaller satellites that are put in constellations. And thanks to the really decreased cost of launchers, putting a constellation of small satellites in orbit has more or less the same mission costs as putting one bigger satellite, but with the big advantage of having a very shorter revisit time. Such large constellations are currently used for defense, agriculture, business intelligence, and disaster management. The most known example of it is probably the OneWeb and the SpaceX Starlink that are aiming both to provide high-speed internet access to places where fiber cables are just economically not viable. And in the graphs on this slide, you can really see the last years, the ramp up of the number of small satellites, which are mainly caused by these large telecom satellite constellations. The technology advance both in telecom and remote sensing have made this possible. For instance, in telecommunications, there have been by the use of ASICs and by using microwave ICs, the transponder size and mass and power have been decreased considerably, providing the possibility to put these devices on smaller satellites. And apart from that, there also has been the development of digitally steered antennas and beam hopping algorithms, frequency hopping, and so on, which have further optimized the use of smaller satellites. In remote sensing, the miniaturization, at least for optical, is a bit less straightforward due to the laws of physics. But in cameras, also the electronic part of cameras obviously can be miniaturized, and this has been done by miniaturizing the readout electronics and the mass memories. And other remote sensing applications using radar satellites have taken benefit also of miniaturization in antenna technology that has allowed now to use really small satellites also for radar imagery. Such telecommunications and surveillance systems are now commercially available, and as I mentioned before, they're also used by governments and by military. because only a very limited number of governments currently has specific space assets available by dedicated military spy satellites or telecommunication satellites. And therefore, while these dedicated assets obviously are very good, secured, very well secured against hostile threats, this is not necessarily the case for these commercial constellations, and therefore the need really also for commercial operators to take into consideration a better securization of their space assets. And what kind of threats are we talking about? Obviously, satellites always have been in a hostile environment from natural radiation, but nowadays they are increasingly at risk by all kinds of threats, threats ranging from really physical attacks where satellites can be destroyed. This can be just by debris, but also by intentional attacks. And there are also softer ways of threat and interference, like signal jamming and interception of data. Which can cause as much damage as real physical attacks. So hence the need really to be aware of these threats and to use also technologies to protect satellites. And so obviously first you have to be aware of the threat, so you have to detect it, and once you have detected it, you can try to remove or mitigate threats. For instance, for natural space weather, or for artificially created electromagnetic pulses to hamper with satellites, you can make your satellites more immune to this by doing a proper shielding and a proper grounding. In order to counteract, for instance, on hijacking of your satellite control, it's a bit more difficult. We have to look in cybersecurity technology. And this cybersecurity is a hot topic for ground networks, but now also more and more for space satellite networks is really gaining a lot of momentum because all operators are concerned with cyber threats on their commercial or military assets. The market for defense IT cyber solutions is already a mature market and is really a competitive market, particularly for commercial systems, while the more advanced operational technology solutions are only beginning to emerge, especially as military investment in space is growing now, and also the focus of cyber capabilities is moving from the software and ground segments also to the on-orbit system level protections, as for instance the cyber hardening of your onboard electronics of the satellite. Another threat to be aware of is hostile interference, and this can be really physical interference as used in orbit servicing technology. So this is technology which is currently commercially available to serve telecommunication satellites in geostationary orbits, to extend the life of these satellites. There are operators that have created satellites which can approach other satellites and attach to these satellites. And clearly this type of technology on proximate operations can also be used for military applications, and either by directly interfering with the satellite, or directly by jamming, for instance, all kinds of signals when being very near to the satellite. So in order to really effectively counter this kind of threats, the real tactical space situational awareness, such as LiDAR technology, can be used on future military satellites. It's probably not something that will be easily adopted on commercial satellites, but definitely on military satellites it makes a lot of sense to do so. Then the threat of data interception can be obviously prevented by encrypting your signals, but encryption obviously has its limits due to the development of quantum computing. And yes, quantum computing is not available yet, but it's not that far away. And this will obviously make all kinds of current encryption technologies obsolete. Now, using optical communication can make your data transmission more secure, because optical communication is more difficult to intercept. Other advantages of the optical communications is obviously that it has a much higher throughput, and the spectrum is unlicensed. So in the very crowded RF spectrum, it's currently very difficult to get licenses for satellite communication. This is not valid for optical communications. If you bring it even a step further, you can create optically quantum encrypted keys, and these can be put into an optical communication network where satellites can be part of, because these optical signals have limitations in transmittance distance on Earth, and therefore by using satellites in such an optical network, you can distribute quantum keys on a global scale around the Earth. The last threat I wanted to mention is the threat of debris, or the threat of collisions, which has always been there, but which has increased remarkably with the number of satellites that humankind has put in orbit, and this has increased the number of debris to very large scales. So the risk of collisions has increased a lot, and a monitoring system to track satellites and debris is then also essential to counteract this. But you can go further, and you could actually fly your satellites outside of the region where there's a lot of debris. And then we're talking about skim satellites. So they are hardly existing today. But it could very well be that their popularity will grow for a number of reasons. So one reason is that it's a bit, let's say, the in-between between high altitude platforms and satellites. High altitude platforms really operating on a local, more on a local scale, while satellites operate on a global scale. But very low orbiting satellites, really flying at the edge of the atmosphere, can come very close to the performance of high altitude platforms, especially for surveillance, because you're much closer to the Earth, or for telecommunications, where the latency is seriously improved if you come closer to Earth. So unfortunately, there have only been 2 successful missions of skim satellites up to now. There has been the Gochin mission, which you see here on the view graph, and there has been another mission from a Japanese mission that has flown also at a similar altitude. I think with these various examples, I've tried to demonstrate the threats that are existing to satellite system and the importance of securization of your satellite assets and space assets in general. Not only for military, but also and even more for small and commercial satellites, as these type of satellites are more and more widely used also by governmental and military customers who are asking more resilience and more security of operations. The small satellites themselves, on the other hand, can be part of this technical solution, as I demonstrated in the case for quantum key distribution networks, in-orbit servicing, and very low Earth flying satellites. So, to conclude, I would say the logo "Keep It Safe" should not only apply to control of the COVID pandemic, but could as well be used to all your satellite control systems. Thank you.